Welcome to this lecture series in group theory. In this lecture, we'll be proving Cauchy's theorem. Previously, we have seen Cauchy's theorem in the context of finite abelian groups, but in this lecture, we'll prove it in full generality, meaning for every finite group. All we need is just some basic theory about group actions. So let's recall the orbit stabilizer theorem. It says that if suppose G is a group acting on a set X, then the orbit of any element little x in the set capital X has size or cardinality same as the index of the stabilizer of that element. The stabilizer of that element is by definition those group elements which fix it. And this happens to be a subgroup of the group G, and hence it makes sense to ask for its index. And the orbit stabilizer theorem says that those two cardinalities are the same. Here is a star mark problem. There is only one problem for today. It's a very simple problem. It says that if you have a group of prime size acting on a finite set X, then each orbit of this action has size either 1 or p. So this is an immediate consequence of the orbit stabilizer theorem and Lagrange's theorem. All right. Cauchy's theorem states the following. Let G be a finite group and P be a prime dividing the cardinality of G. Then G has an element of order P. Note that if we were given that G has an element of order P, then it would have a subgroup of size P, and hence by Lagrange's theorem, the size of the group would be divisible by P. But it is pretty remarkable that the converse is also true, meaning that if you have a prime that divides the size of the group, then the group has an element of order P. And the original proof due to Cauchy was pretty long. It was, I think, more than the paper, I think, was some 8 pages long or something like that. But the modern proof is very short, which is one of the modern proofs is what we are going to discuss. Later in this lecture series, we'll see another proof. But today we'll see a very short proof, which I believe is due to James Mackay. I'm not sure. So here is a general fact which we will need in the proof of Cauchy's theorem. So suppose we have a group of size P. So the group is H, and suppose it acts on a finite set X. So as we already hinted in the problem that if the group has size P and it acts on a finite set, then every orbit has size either 1 or P. So what we are doing is collect only those elements in the set X whose orbits have size 1. So note that this is same as those elements of X. Oops. Those elements of X which are fixed by everything. Just realize that. Not that we need it, but still. So the conclusion is that the size of the set X is congruent to the size of set X1 modulo P. It's actually very easy to prove this, so let's do it quickly. So let O1 up to OR be all the orbits of size 1, and O1 prime up to OS prime be all the orbits of size P. There are only two types of orbits, those with size 1 and those with size P. So we write them down, we enumerate them. And since orbits partition the entire set X, we have X as the disjoint union of these things. So this is just simply because orbits partition the set X. This notation, this kind of square kind of union, is just to emphasize the fact that all the participating sets here are pairwise disjoint. This is just ordinary union, only it is emphasizing the pairwise disjointness of the things. Before I go forward, let me just mention that R is nothing but the size of X1. So please realize that. Right? These are all the distinct orbits of size 1. They are just, each one of them is equal to some singleton for some little x in the set capital X, and those singletons are precisely the elements of X1. So this is something that we need to realize. And now from this equality that we have here, we get immediately that mod x, the cardinality of X, is nothing but the sum of cardinalities of the orbits of the first kind plus the sums of cardinalities of the orbits of the second kind. But what is this? This is nothing but R plus S times P. As we have already commented, R is nothing but cardinality of x1. Let me write that on a separate line. So this is cardinality of x1 plus S times P. And going modulo P, we get cardinality of x is congruent to cardinality of x1 modulo P. That finishes the proof. So it's a very simple proof. And let us now prove Cauchy's theorem. So, all right, so let P be a prime such that P divides the cardinality of the group G. And we want to show that G has an element of order P. So let H be this group, Z mod PZ. And here is the clever, there is we will define an action of H on a certain set, and that is the clever part of the proof. It's not clear how one comes up with such things, but somebody did, and we can enjoy that proof. So here is the definition of X. So let X be the set of all functions. Maybe I should write it as maps from Z mod PZ. Okay, so it's not all maps, it's just some of the maps. So F is a map from Z mod PZ to G such that F 0 bar times F 1 bar dot F P minus 1 bar equals the identity of the group. Yeah, so let me say a few things. What is Z mod PZ? Z mod PZ is, recall, 0 bar, 1 bar, 2 bar, P minus 1 bar. Where what does this bar mean? This bar, for instance, 1 bar means all those integers which leave the same remainder as 1 when divided by P, or equivalently all those integers n such that n minus 1 is divisible by P, and similarly for all the others. So that's what the group H is. And all we are doing is we are considering all the maps from Z mod PZ to G, which have this property that if you product all the things in this succession, then you get E, meaning the identity of the group G. And this is a sort of a complicated way of saying something. One could have defined it equivalently as this. We could have said, consider only those tuples in the p-fold product of G with itself, such that, the product of all of these is equal to identity. So I've grayed it out because this is an alternate description of the above thing, but I will use this description because it is easier for me to deal with when we define the action. But this perspective one should also, keep in mind and see what's going on in this perspective. It's the exact same description, but perhaps this looks a little bit more daunting than this one. So do the work. Please try to connect the two things. It's nothing very difficult is going on. So define an action of H on the set X as R dot F as follows. R bar dot F is a function. So when I say R bar dot F, pick R bar in Z mod PZ or in H, and F in X. F is a function from Z mod PZ to G with this property. Then define R bar dot F as another function, of course. Is defined as follows. R bar dot F, or is defined by writing R bar dot F of something, whatever, let's say maybe I bar is equal to F of I bar plus R bar. So that's how we define it. And what's going on in the gray perspective, in this perspective, is the following. So 1 bar dot G naught G1 up to GP minus 1 is nothing but G1, G2, GP minus 1, GP. So that's just one bar dot something. You can figure out what happens to 2 bar and so on. All we are doing is, what is 1 bar doing? 1 bar is just cyclically permuting these things in the anti-clockwise sense. So G1 takes the place of G0, G2 takes the place of G1 and so on, and G0 takes the place of this last entry. So that's what is happening in the second perspective. But this way of writing is very convenient for me to define the action. All right, and one can easily check that this is an action. The only crucial part to check is that this property is preserved under such things. So how do we show that? So let me just show that maybe in a different color, that 1 bar dot f also satisfies this thing. So this thing. So we want to show that 1 bar dot f times, not times, 1 bar dot f evaluated on 0 bar plus, what am I saying, not plus, times 1 bar dot f evaluated on 1 bar. Looks very ugly, but what can you do? So what is this? This is nothing but f of 1 bar times f of 2 bar. Now it doesn't look ugly. F of p minus 1 bar times f of p bar, but f of p bar is just f of 0 bar. So that's what this is. And this is what we want to show is equal to 1. So why is this equal to 1? Well, this product is equal to 1. But f0 bar up to fp minus 1 bar equal to 1. When I say 1, I mean the identity of the group. So this implies if we multiply both sides by f0 bar inverse, then we would get f1 bar dot 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 fp minus 1 bar equals to f0 bar inverse. And now we multiply on the right by f0 bar. So this implies f1 bar dot 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 fp minus 1 bar f0 bar equals e. So what did we do? From here to here, what we did was we pre-multiplied by f0 bar inverse. So we multiplied on the left so that this kind of cancels out and we are left with this much on the LHS. And now we post-multiplied by f0. So that way we can just move it to the right, and therefore this is the case. So this is indeed an action, meaning what? 1 bar dot f is indeed an element of the set X. Right? And similarly, r bar dot f is indeed an element of the set X. So just make sure that you follow that. So we do have an action of the set action on the set X of the group H. Okay, now what is the size of H? Size of X. The size of X we claim is nothing but this much. So why is that? Basically, here is the argument. You choose whatever values you want for f0 bar, f1 bar up to fp minus 2 bar. So the first p minus 1 kind of entries, you can choose whatever you want. The last entry is then decided by the choices of the first p minus 1. In this perspective, you choose whatever is g0, whatever is g1, whatever you like it to be, and then this you're forced to choose so that this equation becomes true. So since you have a free choice on p minus 1 coordinates, note that this starts with 0. So if you have a free choice on p minus 1 coordinates, you are having cardinality g to the power p minus 1 number of things. So this is a crucial point. And now, if x1 is those things such that orbit of x has size 1, which as we saw is nothing but those things which are fixed by each element of the group H, then by the previous lemma, cardinality x is congruent to cardinality x1 modulo p. Cardinality x is this. But p divides the cardinality of g, and hence this is also divisible by p, which implies 0 is congruent to that guy. Okay, so far, I mean, it's still unclear how we are going to produce an element of order p in the group G. But here is the last point. Note that the constant function mapping into which takes everything to E. Let me just write H is in x1. So we have an element of x1, the function which takes everything to the identity of the group G. That clearly is in x1, right? Because if you, in the tuple notation, it is just e comma dot 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 e, and if you cyclically permute it, you're going to get the same thing. So its orbit is of course just itself. It's a singleton. And now, since P is a prime, and you have a non-empty set, meaning the cardinality of x1 is certainly a positive integer, as we have shown it. X1 is a non-empty set. What we have is the cardinality of x1 is divisible by P. Thus, by the yellow thing and the boxed thing. Oops. So by the yellow thing and the boxed thing, we have the size of x1 is at least 2. You can say much more, but this is all we need. And the size of x1 cannot be 1, right? It is certainly at least 1 because we have exhibited one element in it. But since its size is divisible by a prime, it is at least 2. So let, not f, let's call it maybe, what's a good notation? Let me say phi. Let's say phi be an element in x1, meaning orbit of phi is 1, such that phi is different from f. Right? Since x1 has at least two things, you can choose something that is not equal to this thing. But since phi is in x1, phi is a constant function. Which means it takes only one value. The cardinality of its image is 1. This is what is the the description of x1 is what it is in it is those functions which are invariant under cyclic permutations in the gray picture, and hence it is just constant tuples. It is going to consist only of constant tuples, and which in the function picture is just constant functions. So phi is a constant function, thus phi whatever I bar is equal to, or let me say I bar. Phi I bar is equal to G for all I bar, where G is not equal to identity. Because if G were equal to identity, phi would just become equal to f, but phi is different from f. So this is the thing. But since we have phi 0 bar times phi 1 bar dot dot phi p minus 1 bar equal to E, we get G to the power p equals E. Right, because each of these are equal to G, and hence we have that. And since G is not the identity element, this implies the order of G is equal to P. And that's it. We have exhibited an element of order P in the group G. So it may look like a complicated proof, but it is not. I mean, it's a very clever proof, but it is not very complicated. It is not hard to follow, is what I submit to you. The way I have presented it, it may seem like a hard thing to follow, all the definitions, but just think of everything in the tuple picture and it may become less complicated in your mind. Anyway, I hope this was clear, and with that I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon, the link is in the description below. Thank you for listening, and I'll see you next time.